All right, welcome back. We're talking about programming the solution to difference equations. And really, when we talk about discrete time systems, we're talking about computer programs. And computer programs and signal processing, they're used in control systems and communication systems and audio systems to process signals, to filter things out. And here in this video, you're going to get your first glimpse of what's happening in these software systems. And if it's been a while since you saw the last video was on differential and difference equations, you want to take a look at that video, particularly the end of the video. And in the end of the video, we solved the difference equation y of n equals x of n plus 1/2 y of n minus 1. And we solved that difference equation using the recursive method. We solved, I think, 3 iterations. So here we're going to solve many more than 3 iterations because a computer program can do this in nanoseconds. And you have to give me an input, right? Just like any other system, you have to give me an input. And the input of our example last time was k times an impulse. So it's a scaled impulse function, k times delta of n. And if you remember, we also have to specify an auxiliary condition or initial condition, and we're assuming the system is causal. All right, so in my program, I've got k equals 1. I'm just going to choose a value of that constant. And if I choose k equals 1, then the input is the delta function. And so when I solve this and I get y, then y will be the response to that delta function, i.e. the impulse response. So I'm letting k equals 1 here, just because I have to pick something. Now, I'm going to define x, right, the input. And I've predetermined that I'm going to make a plot of this signal from n equals negative 100 to 100. So, I have to decide on, just like when you plot something, you have to decide on a range of n to plot it. So I'm choosing negative 100 to 100 in steps of 1. So if that's my range of n, and if I want to plot an impulse, then an impulse would be zeros, 100 zeros, corresponding to negative 100, negative 99, all the way up to negative 1. And then it would have a 1 at the origin, that's this. And then it would have 100 more zeros, corresponding to n equals 1, n equals 2, all the way up to n equals 100. So this is my input. This is the x, and times k, because it's a scaled impulse. Now, the vector y is going to hold all of the samples for the output, and we're going to calculate these recursively. So what I'm doing here is I'm initializing y as just 201 zeros. Why 201? Because if I'm calculating this from negative 100 to 100 in steps of 1, there are actually 201 samples, 100 to the left of the origin, 100 to the right of the origin, and the origin itself, 201. So I'm just initializing that all of 0. And remember, we're assuming this is a causal system, so the output is 0 until the input becomes non-zero. Okay, remember causality. The output cannot become non-zero until the input becomes non-zero. So at what sample does the input become non-zero? Well, at the origin, but that corresponds to our 101st sample, right? Because we start at negative 100. So at the 101st sample is when the possibility emerges that y could be non-zero. So we're going to start our loop at this indexer, II, at 101, because that's the first chance that the output has to change to non-zero. And then we're going to go from 101 to the 201st sample, i.e. the last sample. Okay, so this is saying now inside my for loop, with II is going to be 101, this is saying the 101st sample of y is the 101st sample of x plus 0.5 times the 100th sample, right? The previous sample of y, II minus 1. So this is the recursion part. And so this is 0, right? And then the 101st sample of x, that corresponds to this 1, right? Because there are 100 zeros first. Then at the origin, so x is 1. So this is going to give me the 101st sample of y is 1. And then it comes to the end of the for loop, and then it's going to make I equal to 102. And it's going to calculate the 102nd value of y, and that's going to be equal to the 102nd value of x plus 0.5 times the previous, or the y that we just calculated. And it's just going to keep going. I equals 103, 104, all the way to 201. So then when that for loop is over, we have all of the output values from negative 100 to 100, or said another way, we have all 201 output values. So then I'm going to ask to plot it. I'm going to make a stem plot of the input first. So I'm going to plot the n values go from negative 100 to 100, comma. Then I'm going to plot the x. That's the input. Okay. And then I'm going to make a new figure and then plot n, negative 100 to 100, comma, the y, the output. All right, let's take a look what we got. So I'm going to click Run. Okay. So, 1 second. Let me dock these. All right. This is the input. So this was generated by the program. So here's the input. And you see n is down here from negative 100 to 100. And the input is 0. Except at the origin we have 1, right? And then it goes back to 0. So that's the input. That's an impulse. Now the output is figure 2. Here's the output. So the output is 0 until the origin. So this is the causality assumption. Then at the origin we input that impulse. So the output goes to 1, and then 1/2, and then 1/4. Then 1/8, 1/16, 1/32, 1/64, and so on. So we calculated these in the previous video, and so this is the output. This is what we would expect to get at the output of the system that's described by our difference equation. So, being that, I'll show you the input again, being that the input was an impulse, this then would be the impulse response, h of n.